Hi there, welcome back. We have discussed motion in one dimension along the coordinate axes, and recently we discussed motion that's not along either coordinate axis. There are some types of motions, like motion on ramps and inclined planes, that are best analyzed by rotating our coordinate axes themselves. So in this video, we will look at how to determine the components of a vector along a rotated coordinate axis system. Let's begin by looking at this vector in a regular coordinate axis system where the axes are not rotated. What are the components of this vector along the x and y axis? Well, you can see that the projection of this vector along the x-axis goes from 2 to 6. So the x component is simply 4 meters, because x-axis is set in meters, to the right, so it's a positive 4 meters. And similarly, the y-axis projection goes from -2 to -5, and so that points in the negative y direction, and it's 3 units long, so that's -3 meters. Obtaining the projections in this case was pretty easy because the grid lines were provided for us, which helped us figure out where the vector began and ended along each axis. But if we weren't given the grid lines, we would still do the same thing. We would start at the tail of the vector and go meet the x-axis by using a perpendicular line to the x-axis, and then we'll start at the tip and do the same. We'll go to the x-axis in the shortest possible way, which is a perpendicular line, and get those endpoints along the axis. Same thing for y-axis. This line is perpendicular to the y-axis, and so is this line from the tip of the vector. So the method to obtain projections along axes are to extend lines from the tail and tip of a vector to the axes in such a way that your line is perpendicular to the axis. Okay, all that sounds good, but now watch what happens if I grab this entire picture and rotate it. So here I've rotated it by a certain amount, and let's now see what happens. Has anything changed? Yes, of course. The vector is not pointing like it was before, but so are not the coordinate axes. The x-axis is no longer horizontal. The y-axis is no longer vertical. But some things are still the same. X and y-axis are still perpendicular to each other. They always are. Have the components of the vectors changed along this new coordinate axis that's rotated? You can see that if I extend from the tail and the tip to the axes, my previous lines still hold good. They are still perpendicular to the axes. Now this extension is no longer vertical as it was before. The extension to the y-axis is no longer horizontal as it was before, but they are still perpendicular to the axes, and so these extensions are good, and so the components are good. So by grabbing the entire picture, the vector along with the axis, and rotating it, we did not change their components. With all that in mind, our task now is to find the x and y components of this acceleration vector that's given to us in this rotated coordinate axis system. Let's take a look at this figure and understand what is presented to us. The x-axis itself is rotated upward from the horizontal by an angle of 20 degrees. The vector is rotated from the horizontal by an angle of 45 degrees. And the y-axis, as always, is simply perpendicular to the x-axis. So what are the projections or components of this vector along the x and y-axis? The temptation that I see with a lot of students is to do this. There's my x component, ax, and here's my y component, ay. Because we're used to seeing grid lines on a graph paper as horizontal and vertical, that's what we tend to do. But that's not a requirement that we discussed a few minutes ago. The requirement we discussed a few minutes ago was that we had to start at the tail and at the tip of the vector and go to each axis with a line that's perpendicular to the axis. This angle here is not 90 degrees. So that's not the right angle. This angle here, neither of these is 90 degrees, so these are also incorrect. So please resist your temptation to use vertical and horizontal lines. That'll lead you in the wrong direction. So I've cleaned up the errors here, and let's start over. So we got to go from the tail and tip to each axis with lines that are perpendicular to the axis. The tail in this case is already at the origin, so we don't have to extend anything there. So from the tip, I go to the x-axis with a line that's perpendicular to it. And so given that the x-axis is tilted in this way, these are all the lines. Let me just show you some here. Lines like this are perpendicular to the x-axis. Lines that are vertical are not. So I got to start here and go to the x-axis such that I make a 90-degree angle with it. And then the component I'm left with here is my AX. Same thing for the y-axis. I start at the tip and go to the y-axis with a line that's perpendicular to it. So that'll look something like this with 90-degree angle over here. So now this would be my y component. So once I have this geometry right, I can solve for the components rather easily. I have a right triangle here, x component over here, y component over here. This component, remember, is the same as this component. This is just a rectangle with the opposite sides being equal to each other. And I know the hypotenuse. It's 4 meters per second squared. All I need is an angle in this triangle. Let me just outline the triangle with a different color just so we know what we're talking about. So there's my triangle, and I need an angle. Well, I already know that this is a right triangle. This is a 90-degree angle. I need one more angle in this triangle, and knowing the hypotenuse, I can get the other two sides. Well, let's see if we can figure out this angle over here. So we have 45 degrees for this whole thing and 20 degrees up to the x-axis. So what's left after that is this angle. So 45 minus 20 is 25 degrees. So I have that angle. And so now it's trivial using SOHCAHTOA to get the x and y components. So for this angle, the opposite side is over here. The adjacent side is over here. The hypotenuse is over here. So to solve for the opposite, knowing the hypotenuse, I need O, I know H. So the function that ties that is the sine function for the SO part of it. So I get sine of 25 degrees equals the opposite, which in this case is just AY, divided by the hypotenuse, which is 4.0 meters per second squared. And as usual, I multiply both sides by 4.0 to get AY equals 4.0 times sine of 25 degrees, which your calculator will tell you is 1.7 meters per second squared. Now for AX, that's the adjacent side to this angle that we are dealing with. So A is what I need. I know the hypotenuse H. The function that ties them is cosine, ca part of the SOHCAHTOA. So this gives me cosine of 25 degrees equals adjacent, which is nothing but AX in this case, divided by 4.0 meters per second squared, the hypotenuse. Multiplying both sides by the hypotenuse, I get AX equals 4.0 times cosine of 25 degrees, which according to your calculator will be 3.6 meters per second squared. So here are my answers for the x component, 3.6 meters per second squared, and y component, 1.7 meters per second squared. Before we call this done, let's just look at our diagram and see if we got the right signs. AY is positive, so let me put a plus there, and AX is also positive, so let me put a plus there just to remind ourselves that we checked the sign, and that's what we got. Okay, so even though this does not cover a lot of new ground, just tilting the axis ends up creating confusion in terms of how to get the components. So it was important for us to review this because we're going to use this for several problems going forward. In this slice of physics, we learned how to determine the components of a vector along a rotated coordinate axis system. And the key thing to remember in this was, in order to determine the projections or components along the axes, we got to go from the tip and the tail of the vectors to the axes using lines that are perpendicular to the axis, which need not be horizontal or vertical. Thank you, and I'll see you later.